record lectures to post them. It doesn't mean we wouldn't like you to show up for class anyways, but this is just in case something went by too quickly or you wanted to hear my explanation again. I don't know that the sound quality is going to be very good at these first ones because I'm using the mic on the on my Surface Pro. So I've ordered something cheap from Amazon, which may be worse, but we'll find out when it gets here. So according to, I should get it like by Monday. That's so exciting. And I plan to wear it all the time, so across campus I look like a celebrity and stuff, right? All right, so some announcements that I wanted to make. Homework 4 is posted on campus. Wanted to say something about the first question on there. How many people are comfortable entering equations and plotting graphs on Excel? And how many are sort of newbies and not quite as comfortable? Right. So if you're in that category, you want to start that a little bit earlier. Okay. So that first question is basically asking you to calculate compressibility factors for a range of pressures, molar volumes, and temperatures, and plotting them on the same graph. Right. So that means you're going to use one of our equations of state that are 2 parameters, right? And recognize that those are fairly complex equations. So if you try to do all of the calculating in one cell, you're highly likely to have a typo. And it's very difficult to figure out where your error is, right? So my recommendation to you is that you break it up into multiple columns, and that will make troubleshooting easier. And it will save you a lot of time, okay? All right, the other thing, exam 1 is coming up pretty quickly. So if you haven't started to prepare for it, you might want to start thinking about that. The other thing is, from time to time, I've been getting questions about the format of the exams and stuff. There's 2 practice exams posted. Those give you a good flavor, a good sense of, what kind of questions I ask and how they're answered, right? The other thing is, starting next Friday, we'll have our first of 2 review sessions for the exam. So Brian will do it from 4 to 6 in 1104 Gilman on Friday. And then on not Monday, this is February 10th, which is 2 days later, which is Sunday, 410 in 1104 will be run by Melissa. Okay? All right. Do you want me to smile for you? I'm just kidding. So keep in mind, I post these annotated lecture notes, so you can take photos of them, that's fine. But they're available after class, right? So the deadline for requesting an alternative time or accommodations for the exam is today at 2. So if you haven't come and talked to me yet, you need to do that right after class today. Okay? All right. There's going to be 1 bonus point for picking up all of your graded homework prior to exams. All right, so things that we've talked about previously. We've made a pretty big deal, I think, talking about the critical point, right? And hopefully, through Wednesday's lecture and today's lecture and some future lectures, you'll see why that's important, okay? So, things that we've mentioned were the critical point for a given substance has a specific temperature and a specific pressure and a specific molar volume for it. And we expect that to be different for different substances, okay? All right, and then what we also talked about on Wednesday was isotherms. So I wanted to take a moment just to briefly go over isotherms. So this is a phase diagram. I have pressure on one axis, I have molar volume on the other axis. And isotherm means I'm holding the temperature constant, right? So if I start at a very low pressure, we know that we expect substances to be in the vapor phase if the pressure is low enough, right? So as I increase the pressure, what I see is that I have a decrease in the molar volume, right? And that's what you'd expect for gas phase behavior. So this is a constant temperature. I'm at a temperature under the critical point, and I'm increasing the pressure. At some point, we know that we cross the equilibrium between the vapor phase and the liquid phase. At that point, at that pressure, we then have coexistence, right? So this represents the gas phase. This represents, at the same pressure, the equilibrium liquid phase. By dropping a line down to the axis here, this gives me the molar volume of the vapor phase. Correspondingly, on the right side, or the left side, I get the liquid phase. Does that make sense? Okay? Now, if I increase the pressure further, what I find is I go completely into the vapor phase, and we see a pretty abrupt shift and great increase. And this just reflects the fact that we don't expect liquids to be very compressible. Does that all make sense? The only other thing I wanted to point out on here is that we have previously pointed out that the reciprocal of the molar volume is the molar density. So if I look at my molar volume of the liquid phase, that's the same as the reciprocal of the liquid molar density. And correspondingly, my greater value will be 1 over rho for the gas phase. Right? Now I have a family of these, or I can generate a family of these isotherms at different temperatures. As long as my temperature is below the critical point, I'm going to be hitting this coexistence curve, right? And that basically means there's going to be a point at which I have liquid and vapor at equilibrium. Now as I go to higher and higher temperatures, we see that the molar volumes start to come closer and closer together, and they collapse to be the same at the critical point. Right? Does that make sense? And then if I go to temperatures above the critical point, then I'm purely in the critical fluid phase. And I no longer see two different phases. Okay? Make sense? Right. So, again, putting some things in perspective, the ideal gas law, if it's going to apply to this system, is only going to apply in this region, because the ideal gas law only works for gases. The power that's associated with the two parameter equations of state that can be written as polynomials as cubic with respect to the molar volume describe this entire isotherm, right? So we've extended our discussion from the gas phase to the gas and the liquid phase, and as well to the supercritical fluid phase, right? And so that's why these equations of state are so important. Okay? All right. So the other side of this is when we look at these isotherms, what we find is that we can write them as cubic with respect to the molar volume. If we solve for the molar volume, we find that there are 3 different roots. Right? The smallest root corresponds to the molar volume of the liquid phase. The largest root corresponds to the molar volume of the vapor phase. And then the intermediate one has no physical significance. All right? Okay, and then as covered in the lecture that I posted, how many people watched the lecture? Was it fun? Did you watch popcorn? Eat popcorn while you're watching it? It's better than Netflix. I'm going to start charging you guys, monthly. How much is Netflix? Is it $12 a month? How much is it?
At least it's like 8 something.
8 something? I'll charge you guys $4 a month. And you can watch all my videos. All right. But if you're like everybody else, you do realize there's only 2 people in the world that have Netflix accounts, and they just share it with everybody else, right? And who doesn't share their Netflix account? Raise your hand. 2 honest people in this room. Okay? Awesome.
It's like
awesome. All right. So the thing that we saw in that lecture and you saw in the homework is that there's a direct relationship between the parameters A and B, where A reflects attractive intermolecular forces, B reflects repulsive intermolecular forces due to volume, finite size of our particles. There's a direct relationship between those parameters and the critical temperature, pressure, and molar volume. Okay? And these were the results that we came up with in lecture and in the homework. Right? So that led us to state the law of corresponding states. And that basically says that any fluid, gas phase, liquid phase, or supercritical fluid phase, we expect them all to behave identically as long as we're comparing them at the same conditions relative to the critical point. All right? And the only other thing I want to just mention, what we saw in lecture on Wednesday was van der Waal equation, Redlich-Kwong, Peng-Robinson. If we looked at the critical point compressibility factor, we found that each of those predicted a constant independent of the identity of the gas or the liquid. Okay? Specifically for the van der Waal equation, we found that the ratio of the pressure and the molar volume divided by R times the temperature, all at the critical point, gave us a value of 3/8. I've done a quick rearrangement of that. That tells me that the pressure times the molar volume at the critical point is 3/8 RTC. We're going to use that identity today in one of our derivations. Right? So just keep that in the back of your mind. Okay, so one of the things that we've pointed out is that we're talking about being at the same conditions relative to the critical point, so we need to describe what that means. Right? So we're going to introduce something called reduced pressure, molar volume, and temperature. Right? Then we're going to see, and this is going to be sort of ongoing, the significance of the law of corresponding states, and then from there we're going to go to virial equations of state. How many of you have heard about the virial equations of state before? So some of you it's not new to. How many is it new to? So you should enjoy this, right? All right. And then along the way, we're going to be introducing virial coefficients. Okay, so starting point for today. What do we mean by relative to the critical point? Well, in order for us to determine something relative to the critical point, we're going to introduce reduced variables. And hopefully this makes sense. If we're talking about a reduced temperature, it's going to be the temperature that we experimentally measured compared to or related to the critical temperature. All right? So that's our reduced temperature. So whatever the temperature is, I divide it by the critical temperature of that substance. Right? If I'm at the critical point, what is the reduced temperature? It's 1, right? Okay? So if this value is 1, that means I'm at the critical temperature. If it's 0.5, I'm at half of the critical temperature. Make sense? What are the units of the reduced variable? It's going to be unitless, right? Because it's Kelvin over Kelvin. And how many people remember using reduced variables in physics? Few of you, right? You saw that those were unitless. At least normally they are. Okay? All right, we can do the same thing for pressure. So whatever our pressure that we're interested in experimentally or using an equation of state, we reference that to the critical pressure, and then same thing for the molar volume. So V over Vc. All of these are unitless, and they tell us where we are relative to the critical point for a given material. Okay? In section 2.4, what we want to do is show that the equations of state that we've introduced follow the law of corresponding states. So van der Waal equation, and I forgot which one we were going to talk about. RK. And before we go down the path of doing the derivation, I just want to talk about what we're trying to do. So what we want to do is we want to start with our equation of state. So I've got the van der Waal equation there. And in place of the parameter A and B, we're going to try to do some substitutions to get this thing written in terms of reduced variables. So right now it's in terms of experimentally measurable pressure, molar volume, temperature, and then our parameters A and B. Right? And so when I put in this in terms of reduced variables, I expect that my parameters A and B are going to leave because it has to be independent of gas. Right? And then the other thing that we've said in class is that R, the gas constant, has been determined as essentially a unit conversion factor. Right? And so when I write this equation in terms of the reduced variables, which are all unitless, I no longer have need of a unit conversion factor. And so in that case, we expect to see an equation that has no R in it. So no R and no parameters. All right. Okay, so we're going to start with our van der Waals equation. And then previously we know that we have relationships between parameters B and A and the critical molar volume and the critical pressure. So I'm going to rearrange this real quickly. This is going to become B equals V bar C over 3. Very straightforward, right? A will be equal to 3 critical molar volume squared times the critical pressure. Okay? So I now have some things that I can substitute into my equation of state. And that's what we're going to go ahead and do. All right? So my very first one, I'm going to put A in there. So it should be 3 VC squared PC. Okay? Next up, I want to put in our identity for parameter B. That's going to be VC, molar volume at the critical point, over 3. All right? So at this point, I still don't have reduced variables, so I need to do some algebraic manipulation in order to get there. All right? And I'm going to step you through it. So what we're going to do is we're going to divide through by VC times PC. Okay? And then we're going to see what happens there. Okay, so dividing through by PC, or VC, is going to be the same as multiplying through by 1 over PC times P plus 3 VC, PC over V bar squared, right? And then I'm going to bring in the reciprocal of the molar volume, so 1 over V bar C times V bar minus VC over 3, right? So that's the left side of my equation, right? Now I need to do it to both sides, so my right side will be RT over PC VC. Okay? Make sense? All right, so let's talk about what happens. Now, if I multiply this through this formula that's in these parentheses, P over PC, what's that the same as? PR. That's the same as the reduced pressure, PR. So I'm going to write PR, all right? Now I come over to this one, I see, well, I've got PC in the numerator, PC in the denominator. That goes away, all right? So I've got 3 in there. And then the other thing that we see is that we've got VC over V. Whoops, I forgot a squared in there. Did anybody see that? Nobody caught that? If you had, I would have given you a piece of candy, all right? So at any rate, how's that related to the reduced molar volume? It's VR squared, but in the denominator, right? Okay. Make sense? All right. Over here, I multiply this through V over VC. That's VR. VC over VC goes to 1. So I have VR, my reduced molar volume, minus 1/3. Okay? All right. Make sense? I have no A's and B's. Okay? All right, now we look at the right side, right? And we see that we have in the denominator the pressure and the molar volume multiplied by each other at the critical point. So this is where I'm going to bring back what we've derived previously, right? And so what I can do is I can replace this pressure times the molar volume with 3/8 RTC. Okay? So let's go ahead and do that. All right, so I'm going to have RT, all right? And instead of dividing by this, I'm going to just multiply by the reciprocal. That makes sense? All right, so that's going to be times 8/3 over RTC. Okay? All right, what happens to R? It cancels, right? So I'm left with 8/3, right? And what happens to T over TC? That's TR, right? Okay, so now we have, this is the van der Waals equation. We didn't change anything except what our variables are, right? And what we see is that we have no parameters A and B, right? And that tells us it works for all fluids, right? And we have no value of R in there, right? And the fact that we can derive this that is independent of the identity of the gas and it's related to the critical point, this tells us that we're following the law of corresponding states. Okay? So no parameters. No R. All fluids. Okay? Does that make sense? Okay. All right, so we're going to do the same thing by looking at the compressibility factor, because up to this point, we've only looked at the compressibility factor at the critical point, right? We'll look at it at all, and we're going to do the same thing. We're going to start with our relationship. Compressibility factor for the van der Waals equation is given by this expression. I'm going to substitute in for A and B, okay? All right. Okay, so B we know is the same as the molar volume at the critical point divided by 3, right? And then A, which we derived from this, is going to be given by 3 pressure at the critical point times the squared molar volume at the critical point. I'm going to choose to write this separately, all right? And so it's pressure times the molar volume of the critical point squared. Again, that comes directly from this relationship, and we've used the previous state. Okay? All right, so what we can see here is I've got VC, the molar volume of the critical point, versus the one that we're interested in, and that gives me VR, all right? Okay? The other side of this is, we know that this PCVC is the same as 3/8 RT. Okay? All right. The other substitutions that we're going to do, pretty straightforward. I'm going to start with my definition of the reduced molar volume. All right? And I can rearrange that, and that tells me that the molar volume that we're experimentally interested in is going to be VR times VC. All right? So that basically means where V bar shows up, I can replace it with the molar volume at the critical point and the reduced molar volume. All right, so in the numerator, I'm going to have VR times VC, right? And then the denominator, VR times VC. Okay? All right. Before we go on to the next term, let's see if we can simplify this a little bit. I've got VC, VC, VC. That can be pulled out in front. They cancel, right? And so my first term goes to the molar volume that's the reduced molar volume divided by the reduced molar volume minus 1/3. Okay? All right. So the next term we want to look at, I'm going to plug in for the pressure times the molar volume, 3/8 RTC. All right? And I already have a 3 there, so that's going to become 9/8 RTC. All right? What happens to R? It cancels, right? Okay? And so that second term is going to become minus 9/8, all right? And we've got temperature times molar volume, and then the critical temperature and the critical molar volume. So that tells me in the denominator, I'm going to have T reduced and V reduced. Make sense? Right? And again, we ended up with an equation that has no parameter A, no parameter B, and there is no gas constant. Works for all fluids. That tells us this is also following the law of corresponding states. Okay? And that's what that's stated there. Right? Okay, so in the homework you worked with the Redlich-Kwong. How fun is that? Not that fun, is it? Right? So you can see why we're focusing on the van der Waals equation. So rather than going through this analysis and algebra, which becomes quite a chore, I'm just giving you the output. So If I start with the Redlich-Kwong equation and I substitute in and get it in terms of reduced variables, we end up with this relationship. And what we see in this relationship is no parameter A, no parameter B, and no gas constant. That tells us it follows the law of corresponding states. Similarly, we get a result for the compressibility factor. All right, so everything that we've talked about up to this point has been about equations of state, right? We should stop and say, well, what about experimentally? What do we expect to see experimentally? So this graph that's shown here shows the compressibility factor as a function of the reduced pressure for a variety of different reduced temperatures, right? Let me just make sure that I write one thing on here. So this is PV bar over RT, right? So Z, as we've defined it, isn't in terms of reduced variables. This is in terms of the experimental pressure, molar volume, and temperature. And then I still need to use my conversion factor for units, okay? So let's focus on this particular curve, all right? So what I have are a whole mess of different gases, right? And we can see that we've got quite a variety. Water's got strong intermolecular forces, carbon dioxide weak, and heptane, big organic molecule, ethane, methane, nitrogen. So we have a whole variety of different intermolecular forces, different gases that we expect to have different properties. But what we see is that as long as we're looking at the same conditions relative to the critical point, we have the same behavior, right? So for this curve, all of these are at the critical temperature, and this on this axis is the reduced pressure, okay? And of course that holds true for other temperatures, right? So experimentally, we see the law of corresponding states is something that's important and works. Okay? Any questions about that? Okay, so what we're going to do next is we're going to talk about another equation of state called the virial equation of state. Right? And one of the goals of looking at the virial equation of state is to determine intermolecular potentials, that is, the interactions between two or more gas particles. Okay? So we'll say at the outset, determine, or let's say yield U of R, where U of R is the potential between two particles. All right? All right, and what we're going to see is that these virial equations of state are basically series that are in terms of either pressure or 1 over the molar volume. Okay? And it's probably not a bad idea to keep in the back of your mind. As pressure goes up, the molar volume is going to go down. Right? And so as this goes up, the reciprocal of the molar volume is going to go up also. So they track each other. Okay? All right. So it turns out that this is a fairly fundamental equation of state. When we talked about the van der Waals equation, Redlich-Kwong, and Pang-Robinson, we did a pseudo derivation of the van der Waals equation. And then we've introduced the other two equations of state, and those aren't derivable. Those are things that just happen to work. Right? It turns out that the virial equation of state can be exactly derived by looking at interactions between the particles. A derivation of this is beyond the scope of the class, so we're just going to introduce what those are. Okay? All right. So the other thing that we'll say at the outset is these virial equations of state, they're not that pleasant to work with. Right? So we're going to be working with them only on the portions that are easy to work with, and that'll be pretty clear when we get there. Right? So let's write the virial equation of state. So our limit is 1, right? Z equals 1, that's ideal behavior. So now we're going to add terms that account for deviations from ideal behavior. The first term, I'm going to put plus. All right, so this is going to be in terms of the molar volume. Right? My next term will be in terms of molar volume squared, molar volume cubed, and the next term will be reciprocal of molar volume to the fourth, to the fifth, etc. All right? Okay, so I haven't put anything in the numerator yet, so I'm going to go ahead and fill that in. So I'm going to put in this first one, B2V function of t. Okay? And then the next term is going to be B3V function of t. And those of you that can detect a trend, what's the next one going to be? B4V function of temperature. Right? Okay, so just general, what are these? So B generic V function of t is called a virial coefficient. And the reason that I put the temperature in there, and we're going to see this specifically for this B2V, is they are strongly dependent on temperature. So they're functions of t. Okay? All right. So the other thing I want to say about these, the one that we're going to focus on most is the B2V. That's called the second virial coefficient. All right? Before we go further, all I want to do is just mention what the significance of these virial equations of state are. So B2V is caused by, or a measure of, interactions between two particles. And it's attractive and repulsive interactions. Right? So interactions between two particles. All right. B3V reflects interactions between three particles. What do you think B4V is about? Interactions between four particles. Okay? All right. So let's talk a little further. As pressure approaches zero, what's going to happen to my molar volume? I have a gas, right? Pressure goes to zero, molar volume goes up, okay? Right? And at zero, it's going to go to infinity, okay? Make sense? P goes up, P goes down. Okay? All right, so let's take a look at this for a moment, all right? So V bar is in the denominator, and as pressure goes up, that means this number is getting, as pressure goes up, V bar goes down. Is that what okay, I'm talking about pressure going to zero. All right, so as pressure gets smaller, V bar goes up. This is going to go up faster because it's squared. This is going to go up faster still. We all agree with that? Right? So what we can say is that low pressures, these terms will tend to dominate. These upper terms are going to be less significant. We agree with that? Okay? All right. So at low pressures, higher order terms become less important. Okay? All right, well, let's take a moment to just look at what the compressibility factor looks like for a given gas for a few different pressure ranges, right? So specifically, we're looking at argon. We're looking at argon when it's around room temperature, 25 degrees C, right? If we're talking about a pressure of 1 atmosphere, 1 bar, we see that we only need the first two terms in order to describe the behavior. If I go to 10 bar, first two terms are important. The third one, it's there, but it's pretty insignificant, right? So what we can say basically is if we're talking about pressures between 10 bar or less, 2 terms is enough. If I go to like 100 atmospheres, I see that I start to get some contribution from the 3rd and the 4th term, but really I only need to worry about the first 3 terms. Okay? So in this case, 3 terms are sufficient. And if we go to really high pressures, 1,000 atmospheres, 1,000 torrs, we see we have significant contribution of the other terms. And I'd have to go beyond this 4th term. Okay? All right. So we're going to be limiting our discussion to the lower pressure region to keep it simple. Right? Okay, so we've pointed out at the outset that we can write the equation of state in terms of pressure, right? So we're going to have the same limiting value, right? So 1 plus, right? We write it as a series, so I'm going to have a series. We know that when V bar is going up, pressure is going down. So V bar being in the denominator means that we're going to have pressure in the numerator here, right? My next term will be plus P squared. My next term will be plus P cubed, etc. Okay? And then what connects this to compressibility is a virial coefficient. But because we're doing this in terms of pressure, now we have B2P. Still a function of temperature. The next one will be B3P, function of temperature. B4P, function of temperature. All right? So I've introduced another virial coefficient, right? Do want to point out that there is a relationship between the equation of state in terms of pressure and the equation of state in terms of molar volume, and it's pretty straightforward. We're not going to do the derivation. It gets a little bit messy, so we're just going to talk about the output. So B2V, function of T, is the same as R times T times B2P, function of T. Okay? Right. And as usual, if you don't believe me on this, I'm going to send out a document that does the derivation for the relationship between the two. I'm not expecting you to know how to do it, but I just want to make sure that you have the information there, that I'm not lying to you. Okay? We all good? All right, so now what I want to do is look at the relationship between this equation of state and the graphs of compressibility factor that we've introduced previously. So again, I'm going to have X and Y axes. I'm going to put pressure down here. It's going to be in terms of bar. All right. And then I've got compressibility factor on this axis where we have 1. That's going to correspond to ideal behavior. Right. And now what I'm going to do is I'm going to put a real compressibility factor curve on there. Right. And so what we've seen is at low pressures, it's common to have some negative deviation. We pass through a minima, and then we go to higher values. Right. And then the only other thing, T, is constant. Okay. All right. So what we've said is that this series can fit this curve. Right. We're not going to worry too much about the entire curve, but what I want to do is just point out that if we're talking about looking in the limit of low pressures, I can draw in a tangent there, right? And what we see is that tangent is doing a pretty good job at describing the compressibility factor in low pressures. Does that make sense? Okay. All right, so let's look at our equation of state, right? If I'm talking about just describing this portion of the compressibility factor curve, what terms are going to be important? And you're going to get a little bit of a clue here. We're looking at z function of p, right? We're hitting the y-axis at 1, right? So that means that term's pretty important, right? And I have a linear relationship. How many terms do I need beyond 1 to describe a linear relationship? This isn't going to be linear, right? So I need this term, that's 1, and I need this term. And that describes this. Make sense? Okay? All right, so let me blow that up for a moment. All right, so I'm going to just redraw this just for this region. All right, so now I have Z, P, there's my ideal, and I'm going to draw in my line. All right, and what we've established is that Z equals 1 plus B2P times the pressure, right? And that portion of the compressibility factor curve for real equations gives me the linear portion. You agree? Okay? All right. So the other thing to recognize is, what's the slope of that line? It's B2P function of t, right? And because we know there's a relationship between B2P and B2V, that also means that it's going to be B2V function of t over RT. Okay? Right. And basically what that tells us is that we can go into the laboratory and we can measure compressibility factors as a function of pressure. And if we look just at the limit of low pressures, the slope of that line gives us the second virial coefficient. Right? All right, so before we go forward, let's just talk about some specifics. So this graph on the left side shows ammonia at low pressures and the compressibility factors, right? And so this corresponds to 0, this corresponds to 100 degrees, this corresponds to 200 degrees. What we see is that we have the expected linear behavior, right? The other thing that falls out of looking at this graph is that we see that the slopes are different, right? And because the slopes are equal to the second virial coefficient, that tells us that they are a function of temperature. We good? Okay. All right, so let me just write M equals B2P. All right. The other thing that we see is that when we're talking about being at these low temperatures, at least for these examples, we see that B2V and B2V have negative values, right? That's a negative slope. Right? And that negative deviation from 1 we've attributed to attractive intermolecular forces. Right? So consistent with what we've previously talked about with compressibility factors, if I'm looking at low temperatures for a given substance, I see that attractive interactions are important. Okay? And then as temperature goes up, they become less important because we know that the kinetic energy of the particles become larger. Right? All right, so this corresponds to attractive IMF. Okay? All right. And then if we're looking at this and we say, all right, I've got this linear relationship in the limit of low pressures, if the value of the second virial coefficient is equal to 0, what's my compressibility factor going to be? Somebody has to know. It's going to be equal to 1. Who answered the question? Who said 1? Yeah. All right. Feast. I'm glad it wasn't somebody in the back. Well, I'm not glad it wasn't somebody in the back. If it was somebody in the back, I would say Brian. Brian could be our candy delivery boy today. All right. All right. And that corresponds to ideal behavior. All right? And keep in mind, we said for ideal behavior, we have no interactions between our particles, attractive or repulsive, right? And that's what we would mean by B2V equals 0, right? So we're going to be taking some time to talk about the second virial coefficient, right? So B2V, we are going to see, is a function of and depends upon U of R. All right? So I want to just define U of R. That is the potential between two particles. All right? All right? The only other thing I want to define in here is this R. All right? So let's talk a little bit about this figure. So we've said that we're talking about the potential between two particles. So these are the two particles. Each of the particles will have a center of mass associated with them. R is the distance between the two centers of masses of our particles. All right? And if we think about two particles in the real world, we expect that they're going to be tumbling through space. So we're really talking about these two particles approaching each other as they're tumbling and doing their vibrations and all that kind of stuff. And so we need to do some sort of a time average over their dipoles and let them come towards each other. Right? So we're going to talk about the output of a derivation of that sort of thing. Okay? So at this point, I'm just going to state B2V is equal to. Right. And this little section, I'm going to write down the equation, and then when we see something new, I'm going to explain what that is. So we start with minus 2. Nothing fancy there. Right. Next up, we've got pi. Right. Next variable is going to be NA. What's NA? That's Avogadro's number. If somebody could pass the box to Mr. Avogadro. I don't know how to spell Avogadro. All right, so nothing fancy there yet. All right, so the next thing, this is where things get a little bit more complicated. I've got an integral from 0 to infinity, and then you ask the question, what are we going to be integrating over? Well, we're trying to describe the interactions between these two particles as a function of r, so we're integrating over all possible distances. So it's going to be dr, right? R squared is going to show up in there, basically because of the three-dimensional aspect of it. So we're just going to toss that down there. All right, the other portions of this that we need to think about, we have an exponential term minus u of r. All right, so u of r, we've already said that's our potential. So this is where the potential impacts the second virial coefficient. I need to reference that to KBT. All right, how many people have seen this form exponential of energy over KBT before? Right? So we're not going to explain where that comes from right now. We will get to that down the road. Right? But this is a common thing that shows up in physics and physical chemistry. Right? And then that is subtracted from 1, and that's our equation. Right? So the other thing I want to put in here, what's KB? It's Boltzmann constant. Right, and I'm going to write an important relationship that you will find to be potentially useful. Right. It is the same thing as R over Avogadro's number. Right? And so it can be thought of as the gas constant, not per mole, but per molecule. Right? And numerically, you guys, hang on 1 minute. Let me just write the rest of this. 1.38 times 10 to the minus 23 joules per Kelvin. All right? This will be very useful. That's where we'll leave it. Have a nice weekend. Guys, just want to make a little comment. It's 2 o'clock exactly right now. Disruption prior to that creates a little havoc in my mind. I would like to leave class pleasant. So please be more patient. Sure.